Hello, so my name is Mahir, and today I'll be doing a presentation on Mini Project 3, which is implementation and analysis of the LeNet 5 inference engine for MNIST digit recognition. So, firstly, in today's world, digit recognition plays a vital role in many applications. It powers the optical character recognition for text analysis, automates the data entry processes in digitized forms, and enables intelligent systems in critical fields like banking and logistics. Our project aims to implement and analyze the LeNet 5 architecture specifically for digit recognition. By leveraging pre-trained weights and using the MNIST dataset, we seek to replicate its performance and gain insights into how this network can be adapted to FPGA targeted platforms. And speaking about its relevance, so this work demonstrates the practical applications of CNNs in addressing classification challenges, focusing on improving the accuracy in automated systems. Okay, so here we'll talk about the LeNet architecture. So this is a LeNet architecture, and what it is it is a classical convolutional neural network designed for digit recognition. Here, as you can see, it starts with a 32 by 32 grayscale input image, which is normalized for efficient training. And the architecture alternates between the convolutional layers, which extract the spatial features, and subsampling layers, which reduce the spatial dimensions. So as we can see here, the first convolutional layer C1, what it does is it applies six 5 by 5 filters to extract the basic patterns like edges, resulting in six feature maps of size 28 by 28. And this is followed by a subsampling layer S2, which reduces the dimensions to 14 by 14 using the max pooling. We'll understand all these concepts later in detail. Next, the second convolutional layer C3, it uses 16 filters to detect more complex patterns, outputting the feature maps of size 10 by 10. And another subsampling layer S4 reduces this to 5 by 5, preparing the data for the FC layers, which are the fully connected layers. So yes, next we'll come to the FC layer. So as you can see, the C5 layer is an FC layer and it maps these features into 120 neurons, followed by F6, which further refines the representation into 84 neurons. And finally, the output layer predicts the digit class from 0 to 9. So it predicts 10 numbers based on the process features. And this hierarchical structure enables the network to learn and extract the patterns at increasing levels of abstraction, making it highly effective for digit recognition tasks. Okay, now we'll come to our project. So we'll first start with the source files, the core implementation of our project. And first, I would like to start with a layers.c file. So this is at the heart of our neural networks functionality, this particular code. It defines the essential operations that enable the network to process the input data and make predictions. Each function here plays a very crucial role in the LeNet 5 architecture. So as you can see first here, we start with the ReLU activation function, and it is short for rectified linear unit. So this function introduces non-linearity into the model by converting all negative values to zero while keeping positive values unchanged. And this step is critical because it allows the network to learn complex patterns and hierarchical representations that a purely linear model cannot capture. And yes, Professor, I'd like to mention here that all the variables and signals have a number 53 as it is the last two digits of my student ID. Now we'll move forward to the softmax function. And the softmax function is applied at the output layer. Its primary role is to transform the raw scores produced by the network into probabilities. And this function ensures that these probabilities sum to 1, making it possible to interpret the output as the likelihood of each class. And this step is very fundamental for classification tasks as it directly determines the predicted digit. After this, we have the convolution operation. So again, this is the backbone of the feature extraction in the network, and this function iterates over the input image, applying filters and biases to detect meaningful patterns like edges, corners, and textures. These filters are learnable parameters, meaning that the network adjusts them during training to optimize the feature detection. And after convolution, ReLU activation is applied to resulting feature maps to introduce non-linearity. So next we'll move on to the max pooling operation. And what max pooling does is it is a downsampling operation that reduces the spatial dimensions of the feature maps while retaining the most important features. And by selecting the maximum value within each pooling window, this operation makes the model more efficient and robust to minor variations in the input, like small shifts or distortions. And finally, we have the fully connected FC layer, which acts as a bridge between the extracted features and the final classification. Here, each input is multiplied by a weight, summed, and added to a bias to produce an output. This process like transforms a dimensional feature map into a vector of class scores, which are then passed to the softmax function. So yeah, this is our layers.c file. Next, we'll talk about our LeNet.c file. But before this, I would like to show you something. So this is our Vitis HLS. And as you can see here in our LeNet.c file, in our C file, we're including initialized weights and biases. All these are our pre-trained weight header files. So yeah, the pre-trained weight header files, like example, you can see all these are in our source directory. So I'll talk about this. So this contains the learned parameters for each layer of the LeNet 5 architecture, and these values were derived from prior training on the MNIST dataset, and they are pretty critical for the forward pass during inference. Each file corresponds to a specific layer or component of the network. As you can see here, this is the convolution 1, convolution 2, FC1, FC2, FC3. So yeah, the purpose is that the weights capture the learned connections between the neurons or filter values for the convolutional layers, and the biases, these account for the offset in the activation of neurons after applying the weights. So yes, let's move back to our presentation. Yes, so speaking about the lanet.c file, so it is a core implementation of our digit recognition pipeline, and it executes a full forward pass through the lanet file architecture step by step. And we first start by passing the input image to the first convolution layer, where the learnable filters extract basic features like edges and textures, followed by an ReLU activation to introduce non-linearity. And next, the first max pooling layer comes. So as we talked before, it downsamples these feature maps and reduces the computational loads while retaining essential features. And the output of this is then fed to the second convolutional layer, which learns more complex patterns using the 16 filters that it has. And this is again followed by max pooling. And yes, so after this comes the fully connected layers. So in the FC layers, as you can see, the extracted features are progressively refined. FC1, what it does is it transforms the data into it transforms the data into some sort of some amount of neurons, and the FC2 then further reduces it to a lesser amount of neurons. And finally, the FC3 output raw score for each of the digit classes. And yes, the softmax function is also there. So as discussed before, yeah, we already went through what this softmax function does before. And yes, so this is our lanet.c file. Yes, here I'd like to add one thing. As you can see in this last portion, the class with the highest probability is selected as the network's prediction. And overall, this process combines the strengths of all the like convolution, pooling, and FC layers to achieve accurate digit recognition. After this, we come to our simulation sources, and in the simulation sources, we have the main.c file. So it is this code is the entry point of our digit recognition program, and this handles the key tasks of loading input data, invoking the LeNet 5 prediction process, and evaluating the results. So first, as you can see here, we have a function to load a binary MNIST image. And this function here, load underscore MNIST binary image 53, is designed to load a specific image from a binary MNIST dataset file. What it does is it normalizes the pixel values to the range 0 to 1 for proper processing by network. And then we also have label loading. So the load function extracts the correct label for the given image from the corresponding label file, and this helps in validating the prediction accuracy of our model. And after this, we have the prediction loop. Yes, so here's our prediction loop, and we have to define an array, as you can see here, input underscore 53, and this holds the pixel data for each image. Now, I downloaded the test image, and wait, I'll show it to you. So for the test image and test labels, as you can see here in the top two lines, I downloaded test images and test labels from a GitHub repository, and I then had to convert them into raw binary format into .bin files, and then I had to put these .bin files into the csim build directory where our Vitis project is. So yes, we have to copy this file path as you can see here, and then after, so a loop is used to process the multiple images one by one. And here's what happens. So first the image is loaded and normalized, and a sample of pixel values is printed for debugging purposes. Then the LeNet predict 53 function is called, which performs a forward pass through the network and predicts the digit class. And the true label is loaded for comparison. And at the end of the loop, the overall accuracy is calculated as the percentage of correctly classified images. And this value is displayed to give us a sense of how well the network is performing. In summary, this file, what it does is it integrates all the major components of our implementation, including data loading, model inference, and performance evaluation, and it is the backbone of our digit recognition pipeline. After this, let us come to the simulation results. So I tried a lot, but the simulation output failed to correctly classify the given images. Now, for both the images processed, the simulation, even though it was successful, the predicted digit did not match the true label, resulting in an accuracy of 0% as it could not achieve what it was expecting. And there could be multiple reasons for it. So, firstly, there could be that we had very small pre-trained weights and biases in our pre-trained weights files. So, the biases we use for this project are unusually small in magnitude, and this could lead to weak activations in the network, resulting in the model being unable to effectively capture the distinguishing features from the input data. Also, another reason could be the normalization impact. So, the pixel values were normalized to the range of 0 to 1, but the combination of normalization and small weights might have caused insufficient feature extraction in the convolutional layers. Also, the simulation used a very limited data set with just two images for the testing. So a small sample size makes it challenging to properly evaluate the network's performance. And this incorrect result highlights the importance of well-trained weights and rigorous testing. And it is a valuable lesson in understanding how neural networks rely on appropriate pre-training and data preparation. And definitely there is doors are open for further improvements, such as fine-tuning the weights on specific data set. After this, let us come to the synthesis report. So the synthesis was successful and it achieved a timing of 7.649 nanoseconds. So the overall timing is better than the target 10 nanoseconds because of the efficient pipelining and hardware specification optimizations performed during the synthesis. And there is an uncertainty of 2.70 nanoseconds, and this could stem from variations in the synthesis estimates, especially for critical paths involving convolution and fully connected layers, which depend on resource contention as well as routing complexities. Now, yes, as you can see here, there are some violations. So these are II violations, and these occur due to data dependencies. Firstly, these stand for initiation interval II violations, and these occur due to data dependencies within the loops, such as overlapping computations in convolutional layers or sequential memory accesses. And also, if you can see here, the limited resources like DSPs and BRAMs can contribute to this II violations. And one more thing we can observe is that there is a negative slack of minus 0.035 nanoseconds. And this indicates that the loop dependencies and resource constraints are causing delays. For example, the convolution operation involves MAC units that may share the DSP slices, introducing a bottleneck. And yes, so research utilization, if we come to the resource utilization, so we can see that there is a high BRAM usage, which is 181 units. And these are being extensively used to store the intermediate activation, example, the feature maps, weights, and biases. Then we have significant DSP utilization, which is 154 units. Yes, 154. Yes, 154 units. So these are critical for the MAC operations in convolution. And also we have a very high FF and LUT counts. So the large number of flip-flops, as you can see here, 16,593, and LUTs which are 19,478. These reflect the complex control logic needed to manage the memory accesses and activation functions like the RELU. And this is quite characteristic of the CNN architectures implemented on the FPGAs. After this, let us move to the hardware interfaces. So, yes, we use the input underscore 50 feeding the image data and the AP underscore written for returning the predictions in a straightforward hardware software interface design. And also control signals, as you can see here, AP start, AP done. So these are standard for FPGA based designs. And the direct mapping of the direct mapping of the input and the return arguments to hardware ports minimize the latency in software to hardware communication. And yes, so if I have to sum this up, then I can say that the design choices such as pipelining and the number of parallel filters directly influence the timing and resource utilization. So optimizations like loop unrolling or resource sharing were likely limited to maintain a balance between the area and the performance. And after this, let us come to the co-simulation report. So once the simulation synthesis was successful, then we move to the co-simulation, and it indicates a pass firstly. It confirms that the synthesized RTL matches the expected behavior from the C model and ensures a hardware correctness. And as you can see from the performance metric, the initiation interval II is high at 183,938 cycles, and we have an average latency of 183,937 cycles is the average latency. Also, our con 2D underscore 53. So its latency is 13,382, and this highlights its computational demands. Also, compared to this, the simpler operations like pooling and FC layers have lower latencies. So these metrics emphasize the computational effort for the digit recognition and highlight areas such as optimization, such as reducing the IEI and balancing the latency with resource usage. Lastly, we come to conclusions. So in conclusion, this project successfully implemented the LeNet 5 architecture, bridging the gap between software-based models and FPGA hardware. And although the simulation results showed incorrect predictions, they were quite instrumental in identifying critical dependencies like pre-trained weights and parameter initialization. And then we came to the synthesis results. We went through it. It highlighted the resource intensive nature of CNNs on FPGA platforms, particularly in terms of DSP and BRAM utilization. And overall, this project provided a deep understanding of the challenges and the possibilities of deploying convolutional neural networks CNNs on embedded systems and setting a strong foundation for future improvements in accuracy and performance. These are our references, and thank you.